Hello, my name is Aral, and this is my CMP 492 senior graduation project for Bogazici University in fall 2023. My project is about partitioning undirected graphs. This study aims to partition a graph into two equal-sized subgraphs such that the number of edges cut is minimized. In the more general problem, edges can also have weights. Here's an example of different ways of partitioning a graph. On the left, 5 cuts are needed to partition it, whereas on the right, 2 cuts are enough to partition the same graph. Before diving into how we can construct a model to find the best partition for an undirected graph, I would like to explain why we need to partition graphs in the first place. As memory becomes cheaper and the processing power of CPUs increase with technological advancements, the complexity of the problems solved by computers also increase. The classical methods of solving problems with a single-threaded fashion is sometimes ineffective in large problems. For such cases, it is much more convenient to divide the data into several partitions that have equal load so that algorithms on data can be operated in a parallel fashion by multiple CPUs. Of course, parallelism brings the term interprocessor communication to our lives, which is, as you might guess, not desired, because it is time-consuming. In order to overcome this, it is crucial to divide the data in a way that the communication between processors is minimized. In this context, graphs are a great abstraction to model this problem. In this study, the graph partitioning problem is solved using an integer programming model. Integer programming is a popular method in operations research, and it is a special case of linear programming. And in integer programming, decision variables can take only integer values. Minimization or maximization problems involving discrete choices can be solved with integer programming. There are several methods to solve IP models. The most popular method is branch and bound, and it is a tree-based recursive solution algorithm, and it looks something like this. Another popular method is cutting plane method. It iteratively refines the feasible region to find the best integer solution. To construct a software that solves IP models, Groby is used in this project. Groby is an optimization problem solver which works in a parallel fashion. Groby uses both branch and bound and cutting plane algorithms, and this is called branch and cut. Groby can solve linear, integer, quadratic programming models efficiently. And here is the integer programming model for the graph partitioning problem. Given the set of vertices and weights of each edge from vertex I to j, for each edge, we need to decide whether to cut it or not. Also, for each vertex, we need to decide on the partition to assign to that node. With these decision variables, the objective function is the sum of all penalties attained from cutting edges. For the weightless version of the problem, the weights are all equal and they equal to 1. Now, we need to define the constraints of the problem. First of all, for each edge from vertex I to j that is not cut, the partitions of the vertices I and j must be the same. Moreover, the partition sizes must be equal. And last but not least, the decision variables need to be binary, meaning that they can only be 0 or 1. This integer programming model is implemented in Python using GrobyPy, which is Groby's Python API library. And the software for this project can be found at this GitHub repository. The software is tested with various graphs. Here are some runtime data with respect to the graph size and graph density. According to the data, the software can partition graphs of any density when the graph size is less than 50. When the graph size is greater than 50, complexity of the problem increases very quickly, and the software can only partition sparse graphs. On the average, weightless version of the problem takes slightly more time to solve than the weighted version, and the worst cases differ in weightless and weighted versions of the problem. Here is another plot of the runtime with respect to large, sparse graphs with different densities to give an insight of the software's performance. Finally, here are some sample solutions of graphs taken from the University of Florida's sparse matrix collection. This one is called GD96_C. Here's another graph from the matrix collection. And here are the solutions for some random, weightless and weighted graphs generated by an Erdos-Renyi model. For more information about the project, you can check the GitHub repository in the first link, and the references for the matrix collection and the Groby are listed under that. Thanks for listening.